All right, so we're on clip note number 3, partial fractions. There's 2 examples. There's also some information that you guys have that I don't have here. Again, I don't have a Word document. All right, and I can see looking at it from right here on my hard copy, I can see that we need to renumber. It looks like they have number 6 as factor, the denominator. That should be just, instead of 6, 7, and 8, should be 1, 2, and 3. Those are the 3 steps for partial fractions. All right, so for our first example here, we've exhausted all the A-B techniques of integration, meaning we've tried to let u be the denominator to do u substitution, but it doesn't work. So we can easily identify the denominator as being factorable, so we're going to proceed with partial fractions. So we're going to decompose. We're going to factor and then decompose. So in the space that you guys have, let's just factor the denominator. Okay, and I'm going to come down here underneath it and pull that rational function outside of the integral context to decompose. So remember, we put a over one of the factors and b over the other factor. If there were 3 factors, we'd have a, b, and c. All right, let's multiply through by the common denominator, resulting in our basic equation. Okay, so what we did, just multiplied by a quantity x minus 3 and x plus 1, that resulted in us clearing that fraction, which meant if I multiplied by x minus 3 here, it would cancel with this x minus 3, leaving me to multiply a times x plus 1 plus, and then b times x minus 3. All right, let's just go through this and let x be negative 1. Everywhere you see x, let x be negative 1. So 5 times negative 1 is negative 5 minus 3. The result of x being negative 1 takes care of that factor. We can cover that up. It's gone. X is negative 1 here. Do the calculations, we get negative 4b. So b is positive 2. Now let's let x be 3. So back to the basic equation. If x is 3, we get 15 minus 3. If x is 3 here, we get 4a. And this zeroes out. So 12 equals 4a. A equals 3. All right, I'm going to jump back into the context of the problem. Okay, so I'm going to have the integral of a 3 over, I guess that was x minus 3. Things are disappearing. Plus, and I prefer to do separate fractions. You don't have to. Integrals, sorry. Separate integrals, you don't have to. I just prefer it. All right, we can integrate easily. This becomes 3 times, if you pull the 3 out front, it's just u substitution. And I think we see that as 3 times the natural log of absolute value of x minus 3 plus 2 times the natural log of absolute value of x plus 1. Or so we're aware that there's some properties we can apply if we want to. We can move the 3 as an exponent, move the 2 as an exponent, and then with the plus we could multiply them. But for what we're doing, no multiple choices, free response, we're done here. Let's look at example 2. Okay, as an added situation here, notice that we have limits, so at the very end we're going to have to evaluate. All right, the denominator is already factored for us, so I'm going to just pull outside of the problem here, and I'm going to say, okay, this is going to be equal to a over x minus 1 plus b over x plus 2. Okay, I'm trying to ignore the integral symbol here. Let's clear this basic equation. So I'm actually dealing with this outside of the context of the integral. Multiply through by the common denominator. I'm going to let x be -2. This factors, this term's gone away. X is -2 here. This is -3b. B is -1. Let's let x be 1. So back up here, we've got 3 equals x is 1, 3a. X is 1, this term's gone, so a is 1. All right, let's see, a was 1, so it's going to be 1 over x minus 1. You don't have to separate them, I just prefer to. B was -1. Finding an antiderivative, well, that's the natural log of x minus 1. Evaluated from 2 to 3. I'm going to go ahead and pull the negative outside and make it a subtraction situation, minus the natural log of absolute value of x plus 2 from 2 to 3. Don't need a plus c because we had limits. We have to do the evaluation part of the FTC. So natural log of 2 minus natural log of 1 minus natural log of 5 minus natural log of 4. Okay, this goes to 0. So I have the natural log of 2 minus the natural log of 5 plus the natural log of 4. You're done, finished, fine, and everything. But if that answer is not there, I'm just thinking that we could use some properties. You could rearrange. You could put these two terms together first, and this one could be subtracted. So when you add, you multiply. So we could think of this as natural log of 2 times 4 over the 5. If you were to collapse it, this is what it would look like. And likely that would be the choice. All right, we're going to take a look at a couple problems on note card number 4, improper integrals. All right, well, welcome back to another one of my funny note cards, improper integrals. All right, let's find this answer. It could converge or diverge. We'll see what happens. All right, it's an improper integral because of the infinity, so let's rewrite that. So b is going to go to infinity, so we're going to have 1 to b. I'm going to pull the denominator up, get it ready for integration. The integration part of this isn't bad at all. All right, drag the limit through until you're ready to apply it. Reverse power rule, increase the exponent to -1, divide by -1. Evaluate from 1 to b. And I know it's a little more work, but I'm going to go ahead and clean this up. Oh, no multitasking. Okay, the limit as b goes to infinity here. I'm going to clean it up and say that this is -1 over x, 1 to b. Okay, as a matter of fact, I'm going to pull that negative right out front. I'm going to put it right here. I'm going to get rid of it because I only want to deal with 1 over x, or 1 over b minus 1 over 1. Just don't forget it's there. All right, so I've got the negative. Now I'm going to plug in infinity. Well, 1 over infinity is going to go to 0. I'll do that in my next step, minus 1. So that all goes to 0, opposite of negative 1. The value of the integral is 1. So that integral converges. Okay, we might not be able to get through all the calculations on these. I'm just kind of, looking at the time here. But perhaps we can at least get them set up. Okay, so what makes this integral improper is that this lower limit 2 is going to make you divide by 0. So I'm going to have to replace that. So because it's in the lower limit position, we typically use common practice A. So as A approaches 2, and you need a direction, well, this is my lower limit. So my function is in between 2 and 5. So if I'm going to come to 2, I've got to come to 2 from the right. So just think about these being placed on horizontally on an axis, a horizontal axis. And you're going to approach 2 from the right side of 2. I'm going to pull the denominator up, realizing I'm going to have to do U substitution. Not having to bring anything in. Reverse power rule. Increase the exponent to a half, multiply by 2. Take advantage of the bracket for your limits. I'm going to pull the 2 out front and replace my U. I said I was going to pull the 2 out front. There it is. This is the square root of U, so I'm going to put in here the square root of x minus 2. Okay. All right, the evaluation part has us replace in 5, so I'm going to have the square root of 3 minus the square root of a minus 2. Ready for the limit. So 2 times, I can drop the limit, square root of 3 minus. All right, if I'm going to approach 2 from the right, that means a number to the right of 2 would be like really, really close to 2. It would be like 2.1, but then get even closer. 2.01, 2.001 is getting closer to 2. So that difference is getting smaller, and the square root is getting smaller yet. That's going to go to 0. So my answer is 2 square root of 3. All right, let's take a look. Example 3 on the way. All right, so we're returning to an infinity as a limit. We're going to need to do U substitution here. Thank goodness it's not integration by parts. Okay, notice you're going to have to, once you rearrange x squared, maybe put it back here with dx, you're going to have to bring in a negative 3 and pull out a negative 1/3. And I needed to put in the limit too. Ooh. Okay, let me see if I can fix that real quick. Yeah, I think so. Okay, so I needed to rewrite that as a proper integral with the limit. So I'll try and take care of all this right now. So 1/3 the limit as b goes to infinity. There we go. 0 to b. All right, so e to the u, that's all u. Everything else is du. And our derivative is e to the u evaluated from 0 to b. Okay, I'm going to make this a denominator. I'm going to make it 1 over e to the b cubed minus, I'm plugging 0 in, 1 over e to the 0. I'm going to do a little cleanup and then evaluate as b goes to infinity. Oh, maybe I can put infinity in right now. E to the infinity cubed, woo, minus, this was the cleanup I was talking about, e to the 0 is 1. Okay, so in that case, I don't need the limit anymore if I substitute it in. Oh, goodness. So 1/3 of, well, 1 over infinity is 0. 0 minus 1. Okay, and if I remember way back up here, this should have been a negative 1/3. And I'm sure that's something that disappeared on me. So I'm going to put it back here, here, here. Because I thought this answer was a positive 1/3. So it converges to 1/3. All right, let's take a look at number 4. There'll likely be only time to get it set up because this video won't upload then. All right, at first glance it looks fine, it looks normal and everything, but remember that as a BC student you have to pay really close attention to where a function's undefined when you're integrating it, and for this problem we can't let x be 1, and 1 falls in between these limits. So we're going to have to rewrite this using properties of integrals. We're going to have to rewrite it at the break, at the point of discontinuity. So, oh joy, 2 problems in 1. So we'll get maybe the setup on it and then have to maybe touch base together later because it is kind of lengthy. All right, for this first integral right here, the upper limit is the issue. So the limit as b approaches 1. Well, again, if these are horizontal, 0 comes before 1. I'm approaching 1 from the left. That's important. And this goes from 0 to b. The integration part of this isn't difficult. That's going to go back just to the natural log, so that's not really too complicated. All right, looking at the second integral, notice that I want to rewrite this as a proper integral, and I'm going to approach a, or a is going to approach 1. I'm inside the interval, so if I'm coming to 1, I've got to come at 1 from the right of 1. This is a, and this is 3. So I'm going to go ahead and find the antiderivative, which is natural log absolute value of x minus 1. 0 to b. Likewise here. From a to 3. I know this is from the left. You're going to do the evaluation part and then do the limits. Get us to that point right there. So natural log absolute value b minus 1 minus natural log, oh, come back, plug in 0, minus 1 is negative 1, but the absolute value is 1, so that's really just natural log of 1. Natural log of 2 minus natural log absolute value a minus 1. Okay, and we have some divergent situations going here. As you approach 1 from the left, think about those values being close to 1, but to the left of them, like 0.9999. When you subtract 1, you get 0, and the natural log of 0 is going down to negative infinity. So as a matter of fact, this goes to 0, this limit goes to negative infinity, plus, and what happens over here is that you have the natural log of 2 minus this one right here, okay, I believe also goes to negative infinity. Plug in numbers to the right of 1, but close to it. So like 1.0000 whatever. That's going to subtract. The natural log of 0 is still a negative infinity. Okay, and what happens is you just get a divergent situation with these infinities. So we just say the integral does not converge. Right, so I think we need to just stop there, if it even makes it. We'll see. But hopefully reviewing improper integrals has helped remind you about this content.